Welcome everyone. Today we have Seet. He's going to talk to us about things he wished someone had told me before he started learning quantum mechanics. So yeah, over to you.
Okay, so yeah, welcome everybody. So the outline of this talk. So the goals are trying to help the transition from studying classical mechanics to QM and motivating some of the choices made in the conventional description of non-relativistic QM. The structure of the talk will be in 3 main sections with 3 subsections each. And hopefully there'll be a break after the second section at the 30-minute mark. I'm being optimistic, but hopefully we'll get there at 30 minutes. And yeah, ask questions during the talk, especially if you see a mistake. Yeah, a lot of this talk is kind of like interpretation. So there's no guarantee that all of it's right. In fact, I'd be really surprised if all of it was right. So if you see anything obviously wrong, just shout out. Or even if you come up with something interesting that I haven't mentioned, just drop it in the chat, and then yeah, we'll discuss it. So right, okay, section 1, a particle and a wave. So I'm going to talk about the language of plane waves for 6 slides, 5 minutes, matching the classical results, 3 slides, 5 minutes, and Schrodinger's equation, 2 slides, 5 minutes. These are, guesswork. Feel free to jump in anytime. These might become longer. Doesn't matter. All right. So electron diffraction. So the first sign that classical mechanics was wrong was electron diffraction, postulated by de Broglie and first observed in 1927 by G.P. Thomson. It suggests that electrons can be modeled as superposable waves, which is a shock. If you have a classical picture in mind, it doesn't make sense. It's a particle, right? How can it be a wave? Yeah, interesting historical side note. So J.J. Thomson discovered that the electron was a particle. G.P. Thomson's father won a Nobel Prize for that. Then G.P. Thomson discovered that the electron is a wave, and he also won a Nobel Prize for that. So it's one of those funny historical things. So I'm going to talk about notation for a while, and here's a pretty picture. Yeah, it's the same thing. It's evolving in time. So you're looking at a slice of phi, and we're just pushing it through time. I'm going to say plane wave basis a lot in this talk. So what exactly do I mean by plane wave basis? All right, let's imagine this is the same as the previous picture, except it's much less pretty. Right, I have a x and t, and then at every point here, phi has a certain value, complex in general. Now I'll just draw it here like this. Meaning I'm drawing the real part of phi and sticking out of the page into the 3rd dimension. So supposing I have some phi, some wavy pattern, and I'll just claim now that you can decompose it into plane waves. A plane wave is something which is like e to the power of I times a constant times x, where x is a position, the constant is just a constant. This won't be new to lots of you, but I did say that the talk would require no prerequisites, so that's what this is for. And if you have a question, please ask. So I sliced along t, and I did that. Then you can slice along k, your new coordinate, and do the same, decompose into plane waves. So in the end, instead of a function phi in x and t, you get a function, I'll just call it a. It doesn't mean anything, it's just a. It takes complex values on these new coordinates k and omega. A of k and omega is like magnitude and phase of the k omega basis function or the k omega of mode. Right. So this is just a bit of notational intro. But if anything's unclear, just sound off. But yeah, so there's some advantages to doing stuff like this. Like on the left here, you can see the real part of phi plotted in the 3rd dimension against x and t. And on the right here, you can see the magnitude of A plotted in omega and k. And it's just 2 spikes. So yeah, it's clearly some simplifications. I mean, if you want to deal with plane waves, there's some nice things that can happen. Something that looks very complicated actually is just 2 coefficients multiplied by 2 basis functions and just sum them. So that's nice. Okay, so I'd like to talk about the physical interpretation of the wave expression. So here, I'm just going to talk about light because it's something that was well understood even in the early 20th century, since the days of Maxwell, actually, so the end of the 19th century. So this a k omega e power I kx minus omega t, the thing that was in the integral earlier, for light, it's interpreted as the electric field at the point x and t due to the k omega of mode. And if you want to find the electric field, you just sum over all the modes. A k omega was the magnitude and phase possibly. K is just wave number, which means 2 pi over lambda wavelength, and omega is frequency of the light. So all these things have like solid physical interpretations. And you can write down an equation of motion for light. Oh, by the way, I forgot to mention, but I mean, I guess it's clear from context. I'm working in 1+1 dimensions throughout this talk. So it'll just be one space dimension, x, and one time dimension, which is conventional. So valid field configurations, phi, for light will satisfy a certain wave relation, which is like this operator acting on phi to give you 0. That's like a nice form of wave equation, which can be interpreted as a dispersion relation. Dispersion relation means a relationship between omega and k. So that's this. Yeah. So what do we know about electrons? Well, we know much less. Like, okay, the interpretation of this is a question mark. The interpretation of A, K, omega is, okay, it's something to do with the number of electrons in the mode. We know that because when we do the electron diffraction experiment, if we try and describe it using waves like this, the parts where they constructively interfere, there's lots of electrons. So we know that if you make the mode bigger, just increase A, that should go with the number of electrons in some way. And if there's none of it, if A is 0, then presumably there's no electrons. But we don't know the exact functional relation. And then for K, what we know is P equals H bar K. So you can get that from experiment by shooting electrons with different momenta and looking at the diffraction pattern that they make. So if you increase P, you increase K, which is 2 pi over lambda. Omega, we don't really know what that is, and we don't know the wave equation either. We can't describe that, but we know it's something linear in phi because the solutions superpose. Okay, so what can we do with this 2 bits of information that we have? How do we fill in the rest? So we know that a wave packet should behave like a free electron because a wave packet is something like a concentration of A, which is something like concentration of electrons. So this wave packet here moves with a speed v, which is dou omega by dou k, the group velocity. I have the derivation in a hidden slide in case anyone wants to ask about it at some point, but whatever. And a regular electron moving freely has like p over m. So we can equate these two. So d omega by dk is p over m, and we also know that p is h bar k. Sub that in, and we get this. What that actually means is that if we want to write down this electron field thing in terms of plane waves, we're not actually free to choose like any set of coefficients. Like I can't just choose any a k omega that takes values over the entire k omega plane. I can only choose values that lie along this parabola. This wavy line is supposed to indicate like the magnitude of A. It's only non-zero on this dotted parabola, which is omega equals h bar k squared over 2m plus omega naught. Omega naught is a constant of integration from here. Yeah. So instead of like saying a k omega all the time, I'll just say ak. Hopefully that simplifies my notation a bit. So you can ignore like everything that I'm saying here. This is just like just to show how you can go from a dispersion relation to a wave equation. So this is the dispersion relation that we were talking about, and I make the claim that I can write it down as a wave equation like this. And the way I do that is I can, if I just like kind of try and randomly guess how do I pull out an omega from this basis function, I can try and hit it with a dou by dou t. So it'll pull down a omega t, and then it'll expand out like this. And then if I take the like this bit and shift it over to this side, then I should get omega times e power I kx minus omega t. And I do. And I can do the same thing for k. And then I can like do this twice to get a k square. So I get this. And I do this once to get omega. And I subtract omega naught. And if you rearrange the terms, and it's a heck of a job, I can tell you, you get something like this, which is starting to look a little bit more familiar. Okay. So we filled in what omega is. We still don't know what it is physically, but at least we know that it's supposed to be h bar k squared over 2m plus omega naught, where omega naught is a constant of integration, doesn't depend on k. It can depend on x and t though, but we just take it that we're looking at a small enough patch of x and t space that omega naught is a constant, and then we try not to worry about it too much. We're saving up trouble for ourselves, so we'll run into it explosively in like 20 minutes or 25 minutes. But okay. And here's the dispersion relation, just duplicated from here. So we've got something. To recap, what we've done is we model electrons as superposable waves propagating the medium, and we require that P equals h bar k, well, which is V equals h bar k over m. If your potential is slowly varying in the section you're looking at, you take it to be a constant, so take it as a free electron. If we require wave packets to travel like classical electrons, we get the dispersion relation, which we rearrange into the wave equation, which is something that looks like that. Where V is something that depends on omega naught and T. It's something horrible, but we'll run into that later. So we haven't done anything quantum so far. So this is just a wave equation describing a strange medium that simulates electron results. And it's hard to apply and solve problems with it directly. Okay, so that's the end of section 1. Questions?
Sorry, Sean, can you go back to the slide where you derived the equation from the dispersion relations? And I was just confused, where does this d omega dk equals p over m, where does this come from?
So let's say I have, well, okay, imagine there's an e power here. Well, it's not important. So I have ikx minus omega t, and omega is a general function of k. Ikx minus omega naught plus omega 1, k minus k naught, blah, 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 blah. Yeah, I'm just expanding a Taylor series about some value k naught. So I have x minus omega 1 t term here, and then a bunch of terms which, don't depend on k.
Yeah. Okay.
Really, but yeah, quadratically. Okay. So then if I have a wave packet, so that'll be a bunch of waves distributed around. Okay, so notice that the limits of the integration in this case, I didn't go to negative infinity and positive infinity. I made the claim that a wave packet has a small band of wave vectors around a central wave number k naught, and then to first order the bit of it that looks like a. So if I translate, if I go forward 1 second in time, then if I want the shape of the wave to look the same, then I have to go forward by 1 unit times omega 1 in x. So that means that this omega 1 here, which has dimensions of speed, is actually a velocity of the wave packet. And if we try and we go back and see what omega 1 was, it's actually dou omega by dou k evaluated at k naught, central wave number of the wave packet.
Right, okay.
So that's the idea behind the group velocity. And then equate these two. So you get p over m and dou omega by dou k. And then this experimental fact that we determined, that G.P. Thompson determined in an experiment. Yeah, if you vary p, you get this thing in k. The interference pattern changes. Yeah.
Yeah. Okay. Makes sense now. Thank you.
Great. And this, since we're on this slide again, and I have 5 minutes extra from the budgeted time. Yeah, I just like to stress that this is important. So instead of allowing a to take values over all of omega and k for this particular patch of like x and t, where omega naught can be taken to be constant, it's only the parabola. And this is where the physical input comes in. Like everything else is just mathematical description, but the physical input is only allowing a to take values on this parabola. I mean, only allowing it to be non-zero on this parabola. Right, operator algebra, probing phi in space and time. So it's starting to look like I'm going to finish well ahead of time. So if you guys have questions, really please do jump in and stop me. You don't have to wait to the natural point. Just, and if you have anything interesting to say also, because I know there's things that I've missed, and there's things which would be useful for someone who's starting out learning QM that I haven't gone into because of like, just being lazy and stuff. So yeah, if you see something, just say something. All right. Okay. So yeah, I'm going to talk about operator notation and eigenfunctions. 3 slides, 5 minutes. Commutation relations, uncertainty principle. 2 slides, 5 minutes. Okay. All right. I'm not actually going to talk about commutation relations much. I have a hidden slide, but I found that I can't say anything new, so I thought I just wouldn't say anything. Okay. And then changing bases. 1 slide, 5 minutes. You can tell that's important because it's 1 slide and it's 5 minutes. Okay, so operator notation. So safe space helps remind you of classical equivalence. So h hat is defined to be I h bar dou by dou t, often known as the Hamiltonian. P hat is defined to be negative I h bar dou by dou x. Yeah. So h, this is one expression for h, and depending on the problem that you're solving, it will take different forms. Like the physical input is actually in here, right? The Schrodinger equation, depending on what v is. And you can equate this to this. And yeah, that's what's so sometimes these are known as generators. Like h is known as the time translation generator because you can move things around in time in this way, right? This is a very, very handwave. This is notation, right? I'll just say, yeah, you don't have to like it, but you have to use it. So
Can you go into a little bit more into what it means, such as generators?
So if I want to evaluate phi at x t plus delta t, and I have phi at x and t, then what I can do is I can expand the Taylor series. This whole block of things is written as e power delta t dou by dou t. Yeah, it's just notation. And you get I h hat dou t over h bar just from this original definition of h. And similarly for p, there's no minus sign here because this starts with a minus, this doesn't.
Mm-hmm.
So sometimes this is known as the time translation operator. So it moves you forward by dou t, and this is known as the. I've never heard someone say space translation. Yeah, I think it's just known as the translation operator, which is a little bit inconsistent naming, but yeah.
Is there some nice intuition why these operators should work this way? Is this like Noether's theorem, something along those lines?
Not really, no. In this case, it's just a Taylor series. Yeah, there's no physics happening in this slide. So this bit is just yeah.
Okay, yeah.
Mm. All right, so eigenfunctions. So our expression for phi earlier, this thing is in the plane wave basis, which means that it's an integral over some index k, and has some coefficients a, k, and some basis functions e power I kx minus omega t. Yeah, the plane wave basis functions are eigenfunctions of the free particle time evolution operator if omega naught is a constant. So this thing will just be like h bar. Oh, it's here actually somewhere. Yeah, it'll be h bar square k square over 2m. We see that if you apply the free Hamiltonian, which is this thing, you just get something which is like a real number multiplied by the function. In general, it can be a complex number multiplied by the function. But the point is that it's like the same as the function. It's just a constant multiplied by it. So if you work in eigenfunctions of an operator, you can apply the generators easily because it just becomes accumulating a phase. Okay, the eigen prefix is from linear algebra, eigenvectors and stuff. So let's say I have some basis functions, and they're indexed by like k, k1, k2. If they satisfy this, then they're an orthonormal basis. It's an integral over all dx. You get this. Oh, and this t is at a certain time, so this is a constant t. And you can decompose the function phi in terms of a basis for your function space bk. And you have some constants multiplying the, yeah. And if you have some operator that such that the basis functions are eigenfunctions of that operator, then you just get a constant multiply out in front. This is conventional. So a hat means an operator, and a unhat means a number. And usually it's the same, like b will double up here as a, if you want to write p hat and p, usually it means p hat is the operator and p is eigenvalue of some eigenfunction of it. Yeah, not super important. So it's analogous to linear algebra. And so like this is exactly the same as this, and this is same as this, same as this. You run into this a lot in courses, so I just thought that I would mention it. Hermitian operator means an operator such that the dagger of it is itself. Oh, sorry, I didn't define what dagger was. Dagger is transpose and complex conjugate. So this is a row, and this is a row, and this is a column, and yep.
Sean, can you explain the first term in phi equals a1 times b1 not b1 delta x not? What does this mean?
Right. Thanks for that. Okay, so for these t is a constant. It just means at a particular time slice you can decompose phi in a certain way. And what this means is that a basis function, it takes values over all x, right? You can think of it as a column with infinitely many entries and one entry at each x.
Okay.
Yeah. Well, I shouldn't have started from 0, I suppose. I mean, it goes from negative infinity to 0 to infinity.
Oh, okay.
Yeah.
All right.
Mm-hmm.
So just evaluated at t equals 0. Left-hand side.
Oh yeah, sorry. Yes, you're right. Yeah, I put 0 here. Yeah, well, these should all be 0 in that case. It just means at a certain time. It can be, t naught, t naught, t naught, t naught, t naught, t naught.
Okay, I see.
Wait,
Right, thanks.
so So does your vector there have an uncountable number of entries? Does that really make much sense to think about it?
Yeah, not really. But it's just that people will say we'll use a lot of the matrix language in QM. Yeah, eigenvector becomes an eigenfunction. Eigenvalue that's the same. And Hermitian, you see what this is doing, right? It's just taking the first element complex conjugate multiplied by first element, and so on and so forth. And that's what's happening here. So the x element of this guy gets conjugated and multiplied by the x element of this guy, and so on and so forth, all the way down, and they get summed. Yep. All right. So uncertainty principle. Yeah, there'll be a lot of hand waving in this slide. I realized after writing the presentation that I can't actually do this without prerequisites. So there'll be a lot of hand waving. I'm sorry, but yeah, you can look at this picture if you like. So okay, what's on the right here is phase space, right? 1 + 1 dimensional phase space. So this is the playground for classical mechanics. You have some x, and then you want to okay. So I'm working in 1 dimension. So you have x, maybe you have some potential, and then you draw a particle in there, and you want to see how it evolves in time, right? And in classical mechanics, what you do is you can write down Hamiltonian in terms of coordinates and the conjugate momenta. And there's one conjugate momentum for each coordinate. In this case, it's p conjugate to x. And if you have a point in phase space, like maybe here, it gets pushed around phase space according to the gradients of the Hamiltonian, classically. Like in the case of a simple harmonic oscillator, it goes in a circle. And any point in phase space will be borne by the flow around in a circle. In the case of a free particle, it'll just get pushed along in the positive x direction or the negative x direction if it's below the x-axis. So am I making any sense here? If anyone doesn't understand what I'm saying, can you jump in? All right, great, thanks. Okay, so yeah, go to the next slide. Hopefully there's something that'll save me on the next slide. Okay, so one thing you can do is the concept of a stationary state. You can actually try and sketch it in this classical picture. So we can clearly see from the previous one that say if you have a single system with a Hamiltonian, maybe it's a harmonic oscillator, you start it at a particular point in phase space, maybe here, then it'll just be pushed around, right? If you look at the thing as time goes on, it won't be time invariant, right? But if you have an ensemble of systems which are scattered all around this circle, and then you push it in time, it will be time invariant. At different time, we won't actually be able to see what the difference is. Say I have a certain density. Oh, this should be a p. I'm sorry about that. So this is a particular time slice, and I have a density on this plane I call f. Right, it's 0 everywhere except that it takes constant magnitude on this circle, which is an orbit of the flow that's produced by the Hamiltonian. Right, the flow of time evolution is produced by the Hamiltonian. If I go from point 1 to point 2, right? Okay, I hope you believe me if I say that the value of the density at point 2 and the value of density at point 1 are related, and I can get there by pushing arrows around, right? Like the same idea as in the same idea as earlier when I apply some translation things, because this density f takes values over this entire plane, and if I move in this direction, like I should be able to like figure out what the value is nearby to it by going in a certain way with e power I something, right? And I'll just make the claim that it if the magnitude of f is constant on this whole thing, then the phase changes in this way, which is sort of believable, right? This is like a ikx pretty much, right? P over h bar is k. For a density like this to be consistent with itself, if I go one round, if I go from 1 to all the way back to 1, I should get back the same value of f, right? So it means that if I go I over h bar, I go from 1 to itself, the integral pdx, yeah, well, I wrote it here, 1 over h bar integral of pdx should be an integer multiple of 2 pi. Because otherwise, you won't get back the same value of f when you go around. So if you want to know more about this, you can write down these densities as like sections of a complex line bundle, and then you can formalize this very, very specifically. The symplectic potential is a natural choice of the connection form, and yeah, you get this result, and you get the Bose-Sommerfeld quantization condition. So yeah, what I like to say is that particular orbits are allowed. So like for this simple harmonic oscillator, this one's allowed. Another one, which is √2 of the distance away, is allowed. And another one is √3 of the distance away is allowed also, just because of this. And because of that, there's a restriction on the size of the orbit. You can't get like a single point to be a stationary state, like a single point in the phase space with defined p and defined x. The best you can do is like a smeared out thing like this, which has a whole bunch of x values and a whole bunch of p values. Or you can get something like this for the free Hamiltonian. It's just a line. Because if you imagine, like, if I start with a single point instead of an ensemble of systems, it's just a single point here. It has a positive p and has negative x. So as time evolves, it'll just be dragged along this way. So if I want this thing to be time static, then I have to have a density that's constant throughout the whole thing. And yeah, you get a line which has lots and lots of x values. There's a defined p value though. So that's another illustration of the uncertainty principle. All right, questions. I expect you have lots of questions.
So in the equation where you get to n pi, right?
Yeah.
If n, there's nothing saying n can't be 0, right? And if n is
yes,
0,
that's fine. Yeah.
Then but if n is 0, then why can you not have a stationary point in that case?
That's a good question. Okay, there's something called the Veil integrability condition on these symplectic manifolds that I'm using, and it requires there to be a puncture. So you can't actually have a. Well, I mean, it doesn't require there to be, but in this case, it requires there to be punctured. So you can't actually have a thing here.
Okay, right.
Anything else?
So for the free Hamiltonian, if you integrate p dx over that infinite line, then do you get infinity?
Yeah, you do. Yeah. So what that means is that the phase that you accumulate from going from negative infinity to infinity is just like undefined. So you can go from like point over here to point over here, and you accumulate a certain phase ikx. But yeah, if you go from negative infinity to infinity, then it's just you accumulate infinite phase.
Oh, okay.
Don't quote me on the Veil quantization condition. I need to check that. But yeah, where are we? Ah, right, changing basis. Right, one slide which I wanted to spend 5 minutes on. So right over here is just something to remind us of what we were doing. Right, so we have we start off with a that takes values on all of k and omega, negative infinity to infinity for both k and omega. And we decide that oh no, actually we only want values which are on this parabola omega naught plus h bar k squared over 2m. So you just index it by 1, which is k. You can index it by omega also, which is fine. All right, and here's Schrodinger's equation. And remember, I said that we're saving up trouble for ourselves earlier on with the dispersion relation to the Schrodinger equation. So if you actually work out the stuff that was on the slide earlier, you get this expression for for the potential, which is not great. It has a dou by dou x in it, which is extremely not great. And it has its complex valued, which is terrible. But don't worry about it too much because you'll see we'll get around this shortly. For now, just note that if omega naught is a constant, then this is just h bar omega naught, which makes sense. And yeah, right. And we can push structure back and forth from phi to h. So what we're doing all along is we have certain families of phi, which we said were acceptable. Right, we impose this condition that A can only take values on that parabola. You can actually change the families that you're looking at by changing h. And it's most direct when you look at this expression. Right, by changing omega naught, we can change h. And by changing omega naught, we can change phi. So you can put structure back and forth. Like h can go to h plus a constant. And then phi goes to e power negative I constant times time. Or h can become something that depends on time. And you get this. From here, something that doesn't depend on space, crucially, just depends on time. Because the quadratic thing in the space, I had to apply that expression that I said was equivalent to k. I had to apply that twice, so you get a bunch of horrible terms. But for time, to get omega, it's just a linear thing. Yeah, and you can change the phase of phi by constant, so theta naught, and it doesn't affect h at all because it's all derivatives of this thing. So there's a lot of fancy names for this kind of thing. We call it changing the ground state energy, entering a rotating frame, interaction picture Hamiltonian. This is the same math, but it's a different interpretation from gauge transformation, because for gauge transformation you get something linear, then you can just do this. Yeah.
Dan asked whether we can see the stationary state slides where he did, at some point. I think.
All right, fine. Yeah, there's some hidden slides, but yeah, okay, later, sure. Yeah, I'd like to take a short break, like, I don't know, 2 minutes. I mean, if people have questions, you can ask them, but I need to get a cup of water.
So I had a quick question about the gauge transformation you mentioned. What's the physical kind of interpretation that we have behind a gauge transformation? So I remember seeing somewhere that if something is gauge invariant, then we consider it to be a physical, observable thing. But is that necessarily true for this case? Because we can have something is U1 symmetric or U1 gauge invariant, and there's certain things which it's not gauge invariant in.
Yeah, that's a good question. Okay, in this case, this isn't actually a gauge transformation, because these fields have a totally different interpretation. These phi's here are densities, and what we're actually doing, right, is a 1D quantum field theory, right? Not a and the quantum field that we're looking at actually is X. Right? It's not. I mean, it looks like we're not, because of all this like stuff. It looks like phi is a field over here, but actually no, it's just a density. You can think of it as an ensemble of particles, and each particle is labeled by a complex number phi. And yeah, actually, I go into some detail on this later, but yeah, it's not a gauge transformation. And sorry, what's the second part of the question?
Oh right, no, it's just kind of elaborating on. So.
Oh yeah, sorry. Yeah, you said something about physical. Yeah. So the idea is that a gauge transformation is something like a change of gauge is something like a redundancy in our description, right? This is the sort of thing that physicists say. You know, it's like, they just tell you that. But the point is that it's something that happens with a change of basis. So like this, right? And the physical thing that you're looking at shouldn't depend on the basis that you measure it in. So that's the idea behind what they say when they say that observables must be gauge invariant, because otherwise it's not observable. It's just something.
Yeah, makes sense. Thank you.
Cool. Yeah, no worries. Yeah, okay, so we'll move on. Right, diffusion and some field theory at the end. This is very, very optimistic, by the way, 5 minutes. But so we'll talk about diffusion and position eigenstates. 3 slides, 10 minutes. The problem with potentials, as you saw earlier, 2 slides, 5 minutes, and then field theory, 2 slides, X minutes. All right, diffusion. So actually, the Schrodinger equation is actually a diffusion equation. I know it doesn't look like one with the imaginary stuff. You never have imaginary concentrations of particles. But if you replace IH bar over 2m with a D, you get this. Right? And then this is actually a diffusion equation. And here's some stuff to convince you. I know some of you have seen this before, so it's you will believe me when I say that del square by del x square minus del by del t is a diffusion equation. But this is just a little illustration. So if you want to check how phi, which is the real value in this case, just the concentration of particles, how phi changes in time after one time step. Well, you lose something proportional to phi, because it will escape in the negative x direction and the positive x direction. But you'll gain something proportional to the value of phi at this point, but half of it, because half of it goes this way, half of it goes this way. And something here also, half of it goes this way, half of it goes this way. So you get these halves, and just expand them out, Taylor series. You get something which goes as del square by del x square. So if you have del phi by del t proportional to del square phi by del x square, that's a diffusion equation. So Schrodinger equation, diffusion equation. So this mu over here is something, it's the chemical potential. It'll be something like you have two different substrates, right, where these phi particles like to live, and maybe one substrate attracts phi particles more than the other substrate. So the value of mu will be different. Yeah, that's the sort of thing you have in mind. All right, so I'm going to talk about position eigenstates. The basis functions that we were using earlier on were waves, and then they have some coefficients. Well, you can do the same thing with something that is in a fixed position and then a coefficient. This is a very trivial and uninteresting statement, right? This is basically how a delta function works. But yeah, so you can actually interpret this as some kind of coefficient times a delta function, which is the basis state. So if you have delta functions over all of space, you can look at that as a basis for your functions in your function space. You can express your function in terms of that basis. Okay, So like imagine I had some quadratic and then I have some delta spikes, and I let it evolve in time and it'll diffuse out. So if I want to find out what phi xt is, well, this doesn't change. These are just coefficients, but this does change, right? It diffuses out. Like a spike will become a diffuse blob after in some time, and yeah, at time t equals 0 is this. At time t greater than 0 it will be this. And therefore, phi x, it'll be this expression, but with this sub in to the delta. Okay, looking at this now, I feel like I'm off by a factor of 1/2 pi. Yeah, this is, I'm pretty certain I'm off by, yeah, you know what I mean. Yeah, it doesn't matter. Yeah, there it is. Okay, here's the derivation. Well, we know how our plane waves evolve in time, right? We did a whole bunch of derivation for that, but yeah, so you can actually express the delta function in terms of plane waves, and this is like, this is evil stuff. When I first saw it, I didn't accept it, but you just have to believe it. And then yeah, you push it forward in time, and we know how that works, right? You just put a negative I omega t, and omega is this, so you get this, and yep, you get that. So all right, the problem with potentials. So we have this omega naught in our expression here. We're actually very happy with this, right? This is like a perfect recipe. If you want to find out what phi is at some future time, you just take phi at time 0 and just put this heat kernel in. That's what this is called, by the way, heat kernel, and just integrate over dx naught, and you're happy because you can predict all of physics. But the problem is that people will tend to give you problems where they give you a potential instead of omega naught. So instead of telling how the basis functions evolve in time, they just give you a potential and tell you to solve it, which is very inconsiderate, but they always do that. So one thing that you can observe is that at small times, when delta t, like you can pretty much ignore this term. So v is pretty much h bar omega naught for small times. So if you want to look at a small time step, t plus delta t, and you have the expression at t, you can just do this, right? Instead of using omega naught, which they didn't give you, they only give you v, you just put in the v. But yeah, it only works at small time, so you can't happily push it like this one. And the idea is that we have some density phi over here, and to get the density phi x t plus delta t at a particular point x, what you have to do is you worry about contributions from everywhere in this. And the contributions from points further away will be very small, because remember it's a Gaussian. Sorry, this is, I'm still talking about diffusion here. Even though this isn't actually diffusion, you look at it, it's not a so d is IH bar over 2m. If d was in here, it'd be a negative d over 4, right? So it's a Gaussian, and it gets very, very small if you're at a great distance away. So I'm just going to be talking about diffusion. So so something here, imagine a Gaussian wave packet. It's originally a delta spike, but when it reaches t plus delta t, it becomes a Gaussian wave packet, and then it has a little bit of contribution at this x, maybe like this high. But this guy is closer, so it's a delta spike, he's spread out, and it's a bit higher because he's closer. And this guy, yeah, he's right on top of it. So from delta spike, it becomes a Gaussian, and the peak will be here. So you have to sum up the contributions from everywhere in space, and you get the next time step. So this is not super useful, because you can only go like infinitesimal time step. The further you go, the worse it gets, because v isn't actually h bar omega naught. But you can do it repeatedly. You just chain them together, doing the exact same thing, which I mentioned, going from this time step, and then there really should be more arrows here, but I had a finite amount of patience making this slide. So yeah, so you can chain them together and just keep going. And you can do n steps. Supposing that you set capital delta t to be n delta t and let n go to infinity, you get this thing, where s is this. All right, questions? Wait, this is okay with everybody. I must be an extremely talented communicator then. When I first saw this stuff, I was like, what's happening? This is insane.
Can you give some interpretation to what these things are? So, for example, S, what do you think that it means?
Okay, right. So this S over here is actually kx minus omega t. Does that help? Right. I mean, if you think about it, right. Wait, do I have a derivation somewhere here? Yeah. Okay. Okay. So when I got this thing, which you'll now recognize as a as a little infinitesimal piece of that S. You can factor out the t, then you get a x dot squared minus I omega naught here. So what this actually was a kx minus an energy, and k is the momentum. So this is actually a Legendre sorry, I shouldn't. Yeah, it's like a Legendre transform. So you go from energy to kx minus energy, px minus energy, which is Lagrangian, yeah. And the integral of a Lagrangian is known as an action, which is
yes, that's where you get the action from. Yeah.
Right. So special case, if a particle is localized at time t, it means that phi x naught t would just be a delta spike with some phase probably, but we're gonna mod square it, so the phase doesn't matter. So you just get this. Yeah, which is an important thing apparently. So people tell me. Okay, so the reason I call this a one-dimensional QFT is because it's directly analogous to a local n-dimensional QFT. So what you have is this interval from t to t plus delta t, and then at every point you have a value of x, right? And then you want to evaluate an action. The action is a local action, which means that it only depends on x and the neighboring values of x, like x at t minus delta t and x at t plus delta t. You can see it over here actually. It only depends on the two adjacent values of x, where adjacent means in time. And you get a Lagrangian, and then so what this was over here actually is like two operator insertions. You put in the nth x must be at x end, and the 0th x must be at x start, and then you evaluate the e power I over h bar of the action, and you'll get the probability that it went from x start to x end. Yeah, and it's totally analogous to QFT, where instead of x you have phi's, and it takes a certain value at t. So people normally say x, y, z, but I didn't want to confuse it with this x. So it'll be t, q1, q2, q3, possibly. You have a little coordinate patch like this, and the action will be something that depends on phi, dou phi by dou t, dou phi by dou q1, q2, so on, and possibly time if you're unlucky. And then you have things like this, and then and this is not as a partition function, and if you're really unlucky, you'll have things like this also, operator insertions into it, which correspond to like a field configuration at a certain time, and the field configuration another time. And then the idea is that you're trying to see what's the chance of it going from that to that, and the answer is always infinity, because because this dx over here, which I slid over, is actually dx to the infinity times 1 over delta t to infinity, which is infinity. But yeah, you can actually do calculations with it, though, oddly enough. I still don't fully accept it, but yeah.
Wait, sorry, can you just give us that again? Like what the capital D means?
Okay, yeah. So this capital D here is actually all this whole thing with n going to infinity. The way to think about this is that it's integral over all paths, right? Hence the name path integral. So instead of thinking about this like diffusion process over many time steps, what people tend to do is they think of it as lots and lots of particles, and they'll go from like do some zigzag path, and then the way they zig and zag will be this, right? Maybe at x at time t plus j delta t, it's at this point, and at x at time t j minus 1 delta t at this point, and you integrate over all possible xj and xj minus 1. So that corresponds to like any possible path. It's also a funny way of thinking about it.
Okay, yeah. So you have a path which is this collection of xj's, right? And yes, you're integrating over all of them. That's all your possible different paths, and then I guess each integral is just over however many dimensional space you have.
Sure.
Right.
Yeah.
Yeah. Okay. And inside the integral, what you have, this is just your action, right? Where you just approximate your energy, your kinetic energy using xj's.
So in going from the previous slide to this slide, I kind of went from the diffusion picture, which is something sort of intuitive, to this path integral picture when I said x dot, because x dot is not a thing that has any meaning when you talk about diffusion, right? It's just a diffusion process. But this x dot, it means there's a path.
Yeah.
And this x dot can be infinity or 0, negative infinity, because they just zig and zag depending on your choices of xj and xj minus 1 for all the j's. Yeah. So let's see how we're doing for time. And okay, we actually finished on the dot. So for this section, I showed that path integral formulation is analogous to diffusion. And interesting thing is that throughout this entire talk, I still haven't done anything quantum. Right? Everything that I've done is like classical analogies. Yeah, if you want to do like the quantum bits of quantum mechanics, wave function collapse, and like quantum information, and that sort of stuff is just insane and doesn't make any sense. I still haven't understood it after 4 years. So, health warning. But yeah, that's it. Oh, sorry, yeah, hidden slides. Actually, there's a lot of hidden slides, but all right. Maybe a useful tidbit is that if your Hamiltonian is in Sturm-Liouville form, then the eigenfunctions will span the function space. It's a thing that a lot of people take for granted, and they just use it in the physics tripos. In the math tripos, I expect you cover this in great detail. So, there's some stuff about pushing arrows around, commutator relationships. Yeah, it's all just boilerplate stuff. I didn't want to talk about it. This is the same slide, but before I decided to approximate the pushing. Yeah, all right. I guess thanks for coming. Yeah, unless people have more questions, I'm happy to hang around for a bit.
Thanks for the talk. Yeah, anyway, does anyone have any questions? Now is the time to ask. If not, yeah, let's thank Sean. It was a very interesting talk, so yeah, thank you. Yeah, and thanks to everyone for coming. We'll have some more student talks in the future, but nothing's really set yet. So yeah, if anyone wants to give a talk, the timetable is still quite free. Just email me, get in touch. We'll sort them out.